Let's look at solving some NMR problems here. We might have done a couple of these, but let's work through them. So we got Proton NMR here. We're given the formula C8H11N. That's nice right there. What else do we see? Well, I like to work from left to right, and I see, well, this is telling me something cool. 5H down at 7. What comes down there? That must be an aromatic ring. And it's got 5 hydrogens on it, therefore there is one substituent not accounted for, or one substituent on that ring. So I have a mono-substituted aromatic ring. I'm not worried about the splitting because this 5 tells me it's mono-substituted. And then I come down here and I see, okay, integration 2, well the most likely way to get 2 is a CH2. And then it is a triplet. And what's the most obvious way to get a triplet? Well, that would be a CH2 next door. All right. So that seems right. That looks good to me. What's on the other side of this CH2? I don't know. What's on the other side of this CH2? I don't know for sure, but whatever's on the other side of this CH2 brought it down to 3 parts per million. Now, what might bring things down to 3 parts per million? Well, being next to an aromatic ring, yeah, that could be 2 to 3, but also being next to a nitrogen. Nitrogen could bring it down to 3 parts per million. Since I know there is a nitrogen in here, I'm just for right now going to think nitrogen. Okay, so note we have this triplet, so there's 2 neighbors. This is a CH2 with 2 neighbors. That's CH2 right there. The 2 neighbors is CH2. Note here we have another resonance. It integrates to 2, so it's probably the CH2, or could be the CH2, and it's a triplet, so there's a CH2 next door. So that takes care of this. One little hint when you're looking at these spectra. See how this spectrum here, this multiplet here, this triplet, how the inner peak's a little bit taller than the outer peak on the right, but here the left peak is a little bit taller than the right peak in the triplet. What that usually means, and not always, but it gives you a hint that whatever caused this to split into a triplet, that resonance is probably down towards the right. And whatever caused this to split into a triplet, that resonance is probably down towards the left. We call that leaning. This peak is leaning towards the right. This is leaning towards the left. All right. This lean is what it is indicating to me, and it's not always right, that what caused this thing to be a triplet, that resonance is over here to the left of it. It's not this guy here to the right of it because it's leaning to the left. You can't, bank on that, but it's a nice thing to look at. And now, okay, what are we left with? Well, we're left with 2 H's here, but what do we have in our molecule? Note, we've got to connect this benzene ring to something. It can be connected to that nitrogen, or it could be connected to this carbon. The deal is whatever on the other side of this carbon didn't cause any other splitting. So whatever on this side of whatever on the other side here can't have hydrogens on it. And when we add up our molecule, we see we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. Well, there's all 8 carbons. There's our nitrogen. The only thing left is 2 hydrogens, and we know we couldn't have the 2 hydrogens here, which tells us that what's on the other side has to be this benzene ring. But what about those 2 hydrogens? Yeah, they're here on the nitrogen because the nitrogen is missing some bonds. So this molecule, when we draw it better, is just a phenyl ring CH2, CH2, NH2. All right, let's continue on. Let's look at this guy here. Note the formula C8H11N also. Ooh, 5 hydrogens, downfield of 7, there's a mono-substituted benzene ring. Okay. Ooh, let's look at our next thing. It's down at 4 ppm. Well, even though that's a stretch, it's a little bit of a stretch, but the only thing that can bring it down to 4 ppm would be a nitrogen. There's no oxygens here like we would expect. It's 1 hydrogen. So that's a CH. The question is, what are the other 3 things the CH is bonded to? Well, note that it is a quartet. So whatever it's bonded to, there has to be 3 hydrogens. 3 hydrogens, 1 extra peak, makes this a quartet. So whatever it's bonded to is 3 hydrogens. And before you start thinking, well, could it be a CH3? Could it be a CH2 and a CH? All those are possibilities, but let's start adding up our carbons. 1, 2, 3, 4, 5, 6, 7. We only have 8 possible carbons. Here's 7 of them, so there's only 1 possible carbon left. So it's probably going to be a CH3. There's our last carbon there. Now, if it is, one would expect a resonance that integrated to 3, split by 1. If this was a CH3 bonded here, we would expect a peak that integrated to 3 and was a doublet. And as we look down here, there it is. A doublet integrates to 3 down here. So that is confirming that that's a CH3 bonded to this CH. Well, what are we left with? We've got this resonance here. It's small. It's a little bit broad. And we notice when we add up our hydrogens and everything, all we're left with is NH2. So let's just extend that. There's our whole molecule. That looks funky. Phenyl ring, CH, CH3, NH2. And there's that molecule. Realize that's how it goes sometimes. Like, well, it could be this, could be that. And sometimes you just, well, what am I missing and what makes sense? All right, let's look at this one. Note we've got a little IR data here. Not only do we have the molecule, but the IR tells us 1718 wave numbers. That's nice. Well, what does that mean? If the IR says we've got a nice peak at 1718, that's telling us carbonyl. All right, so we know we have a carbonyl in there. Ooh, a bunch of peaks to the left, to the downfield side of 7 that integrates to 5. Well, yes, there's a splitting pattern and we could probably work it out. I don't care. It integrates to 5. There's only one possible beast, a monosubstituted benzene ring. Okay. Now what do we have here? Oh, let's look at this peak here. It's integrates to 2. Most obvious way, a CH2. It's a quartet. Most obvious way, SCH3 next door. And it's down past 4 ppm. What could bring it to 4 ppm? Oxygen. We know oxygen's bringing things down to 4 ppm. So I'm betting there's an oxygen over here. Now, we could be smart or we could grind through it. Which do you want to do? Let's be smart, shall we? Check this out. We know we have a monosubstituted benzene ring. We know we have this carbonyl, and this one peak here told us we have OCH2CH3. When we add up all of our atoms, 1, 2, 3, 4, 5, 6, 7, 8, 9, there's our 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's our 10 hydrogens. There's 2 oxygens. These 3 pieces make up our entire molecule. And as you can see, there's only one way to connect them that makes any sense at all. Connect the benzene ring to that carbon and connect that carbon to the oxygen. So yeah, here's our beast right here. Benzene ring, carbonyl, OCH2CH3, this nice little ester. Okay, you might be saying, hey, what about this peak over here? We never even looked at this one. Yeah, we didn't have to, but let's do it anyway. Recall that this one resonance was due to this CH2. The fact that it was a quartet told us there's a CH3 next to it, which means somewhere in this spectrum we have to have this CH3. We would expect a peak that integrated to 3, since it's a methyl group, and it should be a triplet because there are 2 hydrogens next door. And that's what this guy is. This is this CH3. It's in there, and we could analyze it. We didn't need it because this peak, man, look at all the information this peak gave us OCH2CH3. That's pretty nice. Moving on down another spectrum here. C9H12. Ooh, okay. Oh, but look at this right away. 5 hydrogens, downfield of 7. There's a monosubstituted benzene ring again. And now let's see what we have here. Ooh, okay. Down around 3 ppm, well, there's only one thing that's going to bring something to 2 to 3. There's no nitrogens in here, so whatever this is, it's got to be bonded to this benzene ring. There's no carbonyls that could bring it from 2 to 3. There's no nitrogens that'll bring it around 3. The only thing is this aromatic ring will bring around 3. So whatever this is, it's bonded to that benzene ring. We see it's got 1H on it. So let's just go CH. And the question is, what are those other 2 things bonded to that CH? Well, let's look at our peaks. 1, 2, 3, 4, 5, 6, 7. That shows 7 peaks, which means 6 protons. Well, how do you get 6 protons if you only have 2 groups? Only one way, a CH3 and a CH3. Note that if that were the case, both these CH3s are on this same carbon here, therefore they are equivalent. So I would expect to see these 3 split into a doublet by this one, these 3 split into a doublet by this one, but since these 6 protons are equivalent, you should see 6 protons split into a doublet by this one. Here it is, 6 protons split into a doublet, 6C1. And this is something just to be aware of, just to get in your head for the future. I call this a screaming isopropyl. Anytime you see 6H and a doublet, you should be thinking, wait, 6 protons split by 1, that's an isopropyl group. I should expect somewhere to see a small resonance that integrates to 1 with a bunch of peaks. And there it is. So whenever you see this 6H doublet and then 1 peak with a 1H with a bunch of peaks there, that's screaming at you isopropyl. We'll clean this up a little bit. Phenyl ring and isopropyl group. Okay.